Welcome. Let's begin our conversation on differential equations. I think the first thing that would be the best to do would be to define what a differential equation is. So I have defined a differential equation. You'll notice in this course I will often denote a differential equation as a dE. And that is going to be an equation involving an unknown function and its derivatives. So essentially speaking, in like your high school algebra courses, you would have an equation with variables and you would solve for x and you would obtain a number at the end. So now what we're going to be doing is we're going to have we're going to have functions and derivatives. And what we want to do now, instead of solving for the algebraic number, is we're going to be solving for the function. So that's a big part of what we'll be doing here. Within differential equations, there's two big types. The first one, a dE, is an ordinary differential equation, and we'll denote that as ODE. If the unknown function depends on one independent variable. So basically, if y is a function of x and there's derivatives, that would be an ordinary differential equation. In this course, we will be focusing solely on ordinary differential equations. I do have partial differential equations defined below as the unknown function depending on two or more independent variables. So if we had a multivariable function and its derivatives, that would constitute a partial differential equation. Solving partial differential equations are a completely different beast. If you have an opportunity to take a course on partial differential equations, I highly suggest it. It was one of my favorite courses in college. Let's go ahead and go over some examples of ordinary differential equations. So for the first example, we have dy dx plus 5y equals e to the x. And the second example, we have y double prime minus y plus 6y equals 0. So these are written in two different notations, and in differential equations, you're going to see this a lot, so get comfortable with the different types of notation. So in this first example, this is written in Leibniz notation. And his notation is the ddx notation. Differential equations can also be written in, I'll call it prime notation here. It comes from a mathematician, Lagrange, so it's actually Lagrange prime notation. There's a third differential equation here, which is dx dt plus dy dt equals 2x plus y. So the big moral of this differential equation is that an ODE can have more than one dependent variable. ODE may have more than one dependent variable. Perfect. So those are just some examples of ODEs. You're going to be seeing many more as we dive into this course. And once again, we define partial differential equations, the unknown function having two or more independent variables. While we're not going to be focusing very much on partial differential equations, I did want to give a little example. So these are actually the same equation. This is written in what we call subscript notation. And we use subscript notation whenever we're doing things with partial derivatives, which we will do from time to time in this course. But what this equation is, it's a very popular partial differential equation. It's easily solvable. It is the Laplace equation. And if you're curious what this equation models, you'll just it models the steady temperature um, of an object on on a rectangular surface plate. That's one of the applications. There's many different applications to the Laplace equation. All right, so we've defined what a differential equation is. We've gone over the difference between an ODE and a PDE, and I've given you some basic examples. Another way we classify differential equations would be by what we call the order. And the order of a differential equation is the order of the highest derivative in the equation. For example, we're asked to determine the order of the dE y double prime plus 5 times y prime cubed minus 4y equals e to the x. Just to clarify, it is y prime cubed. It is not the third derivative of y. Students do mess up, especially as notations do get varied. It's something that I would like to trick students on an exam, so do be aware of it. But basically, what is the order of the highest derivative in this equation? It's 2. So, the order of highest derivative is 2. And therefore, this is a second order differential equation. Beautiful. So we'll classify differential equations by order. We'll also classify them based off of if they are linear or not. So we say that an nth order ODE is linear if it can be written in this following form. So it's basically an, which is a function of x, times the nth derivative of y, plus a to the n minus 1, which is a function of x, times the nth minus 1 derivative of y, all the way to a naught y equals g of x. Basically, g of x and each aj depends solely on the variable x. Otherwise, it would be a non-linear ODE. I do have a few examples of linear ODEs. So for example, y minus x dx plus 4x dy equals 0. We can actually go ahead and rewrite this equation to make it look like the form in the definition above. So this can be rewritten as 4x dy equals, well, we're subtracting it, so the signs are going to flip here. X minus y dx. And then we're going to do 4x dy dx equals x minus y. So this looks really close to what we have here. To make it really look like our definition, we're just going to move the y term over. So we have 4x, I'll call it y prime, plus y equals x. And this definition does satisfy our linearity term, so we're good to go. Clearly, the second one, y double prime minus 2y prime plus y equals 0, that is definitely linear. There's no questions there. And also y triple prime plus xy prime minus 5y equals e to the x, that does satisfy our definition. I want to make this crystal clear because this does mess students up on an exam if I ask them if a differential equation is linear or not. Independent variable dependence is okay for linearity. So since this is a function of x, as well as this, we are all good. It is okay for linearity. So independent variable dependence is okay for linearity. Really hitting that point home. Now, I do also, since we went over some linear ordinary differential equations, I have some examples of nonlinear ones, and we'll go over why each one isn't linear. So for example, for the first one, we have 1 minus y prime plus 2y equals e to the x. Well, the issue for the first one is that the coefficient depends on y. Coefficient depends on y. The second one, we have y double prime plus sine y equals 0. The issue with this one is that sine y is a nonlinear function of y. Sine y is a non-linear function of y. Perfect. And then now we have, this is not a mistake. This would also be a good exam question to trick you on. So you have the fourth derivative of y plus y squared equals 0. And just to emphasize and to repeat, notation is everything here. So y squared is a nonlinear function of y. The power of y is not 1. So this is why this ODE is nonlinear. Not a linear function of y. Power is not 1. All right, so we've classified differential equations so far through ODEs versus PDEs. We've gone by the order and by linearity. So one of the biggest things that we're going to be doing in this course is solving differential equations. So let's go ahead and define what the solution of a differential equation is. So, definition. A solution of a DE in the unknown function y and the independent variable x on a given interval I is a function that satisfies the differential equation identically for each x in the interval. The part that I want to stress, it's going to be for all x in I, and it's defined on an interval. So you have to be aware of, for the most part, you don't really need to think about the interval too much, but I do have an example here where the interval does matter. So, yep, that is the definition, and let's go over a couple of examples. For example, suppose that you are asked if y equals c1 sine 2x plus c2 cosine 2x, if that is a solution to the differential equation y double prime plus 4y equals 0. Obviously, we're going to know how to solve these equations later in the course, but there are ways that we can use our single variable calculus to determine if this is a solution. So what we'll do, so we know what y is. Y is c1 sine 2x plus c2 cosine 2x. Let's just take two derivatives of this. So we have y prime, and that's going to be equal to 2c1 cosine 2x minus 2c2 sine 2x. All right, and then let's go ahead and compute one more derivative. So y double prime, that's going to be equal to, well, negative 4c1 sine 2x minus 4c2 cosine 2x. Once we have computed the derivatives, we're just going to plug it into the equation. So this implies that y double prime plus 4y, and let's just plug it in directly. So we have negative 4c1 times the sine of 2x minus 4c2 times the cosine of 2x. Then we're going to have plus 4 times, well, y, which is c1 sine 2x plus c2 cosine 2x. So notice that the 4 distributes both out to the c2 cosine 2x term and to the c1 sine 2x term. We have negative 4c1 and negative 4c2, positive 4c1 and positive 4c2. As you can see, this is going to come out to 0, but I really want to emphasize the point even more, so I'm going to be tedious with this. So we're going to have negative 4c1 plus 4c1 sine 2x plus negative 4c2 plus 4c2 cosine 2x. Now this is flamboyantly obvious that it is equal to 0. And now what we can conclude from this is that y equals c1 sine 2x plus c2 cosine 2x is indeed a solution to the differential equation y double prime plus 4y equals 0. So y equals c1 sine 2x plus c2 cosine 2x solves y double prime plus 4y equals 0. And that is our solution for this stage of the game. All right, let's go ahead and do one final example with this lecture. So what we're going to do is we are going to show that the relation x squared plus y squared equals 25 is an implicit solution of dy dx equals negative x over y. But the difference in this example, we are going to determine all of its intervals of definition. So basically, where is the function defined? So the first part is going to be pretty straightforward. We're just going to be doing implicit differentiation, and then we'll decide based off of what we get where the function is defined. So go ahead and start by doing our implicit differentiation. And when we do implicit differentiation, let's not forget, basically we just do ddx of both sides. So ddx of x squared plus y squared is equal to dx of 25. And now we'll take the derivatives of both sides. With respect to x, so we have, for the first part, we have 2x plus 2y. Now we're going to use the chain rule here because y is a function of x, so we have to do 2y times dy dx. And then the derivative of 25, that's quite easy, that's just 0. Next, we'll go ahead and do some simplifications here. So we have 2y dy dx equals negative 2x. And then we'll divide both sides by 2y. So at the end of the day, we get dy dx, and that is going to be equal to negative x over y as desired. So now what we want to do is we want to determine all of its intervals of definition. So when is this differential equation valid and when is the solution valid? So observe that x squared plus y squared is equal to 25. Basically, our big thing here is the denominator cannot be 0. So this is what's going to dictate what our interval, where the valid intervals. This is going to dictate the valid interval is the fact that this denominator, which is y, it cannot be 0. So we have x squared plus y squared is equal to 25. This is going to imply that y is equal to plus minus the square root of 25 minus x squared. And when we take a square root, it is basically going to mean 25 minus x squared. So if you recall the domain of a square root function, it is greater than or equal to 0. However, since the denominator of y cannot be 0, then it has to strictly be greater than 0. So for a typical square root function, it would be greater than or equal to. But since the denominator cannot be 0, it must be strictly greater than. So I'm going to make that crystal clear right here. And then this happens only if the absolute value of x is less than 5. So in conclusion, the interval of definition for this differential equation, along with its solution, is going to be the open interval -5, 5. And there's our answer. All right, so we have gone ahead and defined the basic definitions of differential equations. We have classified them between ODEs and PDEs. We've gone over order and linearity, and we've gone over verifying solutions, as well as determining the intervals of definition. That concludes this lecture. Attached to this lecture, I will have the solutions from homework 0. So if you want to take a look at those, please feel free to do so. And if you have any questions, you can go ahead and email me at any time. Thank you very much, and we'll see you next time.